Hi, everybody. Welcome to our session at SCI-Arc. Today, we will talk about materials and systems after the Eaton fire. So SCI-Arc, we're located in Los Angeles. We're an architectural school in the Arts District. And we have this task force with our faculty and key professional partners, the Resilient Futures Task Force. We've had 2 events. This is our 3rd event. And today, we have a panel of experts and specialists that we have curated with faculty member At.Herwig Baumgartner and myself, Sophie Pennetier. So today we have a 2-hour event to talk about the materials and systems. We have a panels of 3 specialists, so we'll have presentations by our specialists who will introduce themselves in a moment. And this, as I was saying, this event is brought to you by our Resilient Futures Task Force in an event created by At.Herwig Baumgartner and myself. So we'll have a 40 minutes panel, 40 or so, followed by a long Q&A. We have attendees here in the audience, and we also have a Q&A on live, so anybody online can use the chat function to ask questions. And this is what we'll be doing today. So we're going to start with a very short, in a few words, introduction by all of our speakers here. And I'll introduce myself last, and we will do the presentation after this introduction. So Nate, hi. Do you want to introduce yourself?
Sure. Good afternoon, everyone. My name is Nate Wittasek. I'm a professional engineer in California and 9 other wildfire states. I've been working in the engineering community here in California since 1997. Prior to that, I was East Coast and was a firefighter while I was going through school effectively, and then did research for Coast Guard and have moved out here and have been enjoying building fire engineering. I'm a principal at Simpson, Gumpertz, and Hager. Thank you.
Hello, my name is At.Alexander Sexsmith. I'm an architect. I'm currently based in Tucson, Arizona, but I'm a graduate of SCI-Arc and from the master's program in 2005 and lived in Los Angeles for about 20 years. Most of that practicing for firms big and small. And it was in 2017-18 that I had to deal with a water-damaged house, which in my case meant black mold. And I started on a journey, a deep dive into really understanding more resilient and regenerative materials, basically materiality for the healthiest home that I could build or the healthiest buildings that I could build. And so have been practicing both residential and institutional architecture along with this course of research, and was generously invited by Sophie a few months ago, and happy to be back.
Hi, my name is At.Kishani De Silva, and I'm a professor at Woodbury University. I also am a project management consultant and advisor with my own consultancy, 2A+D Management Services. We at Woodbury designed and built the first permitted 3D printed dwelling in Los Angeles with a special focus on climate resilience. And given our context here in Los Angeles, a real deep dive into fire resilience. And again, Sophie and I have collaborated on a few other things together, and she invited me to be a part of this panel. Since there are lots of strategies, as you will see as we go along, that we incorporated into the design and construction in terms of climate resilience.
Hi, I'm At.Herwig Baumgartner. I'm an architect based here in Los Angeles with Baumgartner Architecture as my firm. I came here to LA in the mid-90s. I spent about the first 10 years here working for Frank Gehry on many projects, including Walt Disney Concert Hall. And then mid-2005, 2007, then started my own firm. And at the same time started teaching here at SCI-Arc, and have been teaching here since. I teach design studios here, but also I'm the applied studies coordinator of the program that's, I guess involved with the nuts and bolts of architecture. But one part that we have been heavily focused on is I also run the robotics lab here. And so we have been, over the last 5 years or so, done intensive research with materials, fire-resistant materials, including 3D printed ceramics with robotics. We'll show some work from the students here today as well. So,
and Herwig is also my boss. And I am a structural engineer by training. And here at SCI-Arc, I'm a faculty. I teach statics, structures, facade tectonics, which is an introduction in building physics, and also a seminar on embodied carbon, where the students learn how to measure and reduce the carbon footprint of their designs. And I'm also the founder of At.The, a consulting firm that provides life cycle analysis and environmental product declaration consulting for manufacturers. With that, I'm gonna tell you more about this panel. The first presentation by Nate will cover nuts and bolts of fire designs and what we all learned from the fire in terms of fire protection and design. Alex will talk about those biomaterials, as Ian mentioned, and Kishani will talk about the permitting of novel construction methods, specifically in the Los Angeles area. And at the end, we will have Herwig, as he said so. So with that, I'm going to let you get started, Nate, to talk to us about the nuts and bolts of fire design.
Thank you. Thanks, Sophie. So in the last 10 years, we've definitely seen an uptick in terms of the amount and size of the wildfires that we've been experiencing. And obviously, even though this year, the acreage that was involved here in the Los Angeles fire, I think it was around 56,000 acres. It's just a drop in the bucket. The value or the loss value of that fire is significant. They estimate that after all is said and done, we may experience a $250 billion loss from that fire. But the trend is clear that we are experiencing significant increases in what is happening in terms of what's burning and the value of what's burning. Part of the reason is that we're dealing with this wildland-urban interface. The wildland-urban interface is the area where homes meet with vegetation that is typically unmanaged. In California in particular, we have a significant threat because we have a great deal of unmanaged vegetation and we have significant, urban populations. It's estimated that about 45 million residences are at risk in the United States, and several million here in California alone, and many of those homes and businesses are high-value homes and businesses. The goal today is to talk about materials, though, and the interaction between materials and resiliency. It helps to understand what's happening. Again, interestingly, Alaska has the highest number of acres, but there are very few people there. The threat is really about the relationship between where you have the most people and businesses combined with the most fires. And that's where California, with our Mediterranean climate, creates a particular risk that we need to watch out for. You can't talk about materials without discussing how wildfires ignite homes in the first place. There are three main mechanisms by which wildfires will cause a structure to ignite. The first is direct flame contact. That is where you have flames from something attaching to your home, from plant matter that's right up against the home, a fence, or you can even have a large structure within a few feet that then the flames lean in the wind and literally pilot an ignition on your own home. Embers are a function of convective heat transfer, and the issue with embers is that these fires can drive embers as many as 22 to 29 kilometers, believe it or not. We definitely had ember travel of several miles in the last fire, and some of these embers are large enough that they will ignite and cause spot fires throughout communities. Then we have radiant heat and flames. Radiant heat is really what you think about when you sit in front of your fireplace and you feel the warmth of that heat. Well, in the case of these homes, it may be 100 to 1,000 times that for a prolonged period of time. And what that results in, of course, is this idea that you can actually cause a spontaneous or radiative ignition of an incident element. All three of these come together in a wildfire in the wildland-urban interface. In terms of non-combustible material strategies, we think about the exterior envelope of the structure. Non-combustible is one of the higher levels of protection that you have to consider when you have elements that are very close to you that can produce a great deal of heat. That could be your neighbor's house. That could be a shed. This is one of the ways we can rebuild to protect ourselves against those imminent threats. We've heard the term Class A roof. A Class A roof is a roof assembly that is designed to withstand many wildfire threats. It may or may not always withstand a conflagration when you have all the homes in the community burning. But if all the homes in the community are provided with Class A roofs and appropriate protection, then the odds of those conflagrations go down dramatically. Performance under fire, things like non-combustible and siding and soffits can resist these kinds of ignition, but they're not the be-all, end-all. We have to think about the details whenever we talk about materials. The assemblies are what get us there, and so part of the discussion has to be not just what you're building the assembly out of, but how you layer it. Assemblies, whether they be roof assemblies or wall assemblies that are constructed of many layers that work together, have been shown to perform significantly better under the threat of wildfire and any kind of fire than single layer assemblies or assemblies that are not a composite. You don't have to use non-combustible materials to be resistant, however. We can use elements like wood, and we'll hear about other materials today that have incredible fire resistance. A fire retardant treated wood is not just a wood that's been sprayed with something to make it fire resistant. It's a wood that's been pressure impregnated with salts. It inhibits chemically the ignition, and it also will essentially stay fire resistant because of that pressure impregnation. We can also use materials in their native form, but that are larger dimensions, mass timber, heavy timber. These materials are now even being used for high-rise buildings because they provide a high level of fire resistance through the mechanism of char. Traditional wood siding can resist ignition for short periods of time. So if you have separation between your neighbor's home or your neighbor's business and your home, you can actually use a normal material, and you just need to think about what's called stagnation, which is where the embers will collect as they hit the side of the home. So design best practices consider how the fire behaves in combination with these materials. This is the vegetation zone. And if you don't address the vegetation zone, even though it's not materials, it's very difficult for any materials to survive. In other words, you can't consider resilience in a wildfire without considering the vegetation density and type of plantings that are around the home. Within the immediate zone, 0 to 5 foot, you really want to keep most things that are over a couple inches out of that zone. The reason is because that's how you get flame impingement. And it's like lighting a match and, lighting a fire in your fireplace. But if you simply create that zone, you will see in today's presentation what the effects of that can be. The intermediate zone is between 5 and 30 feet. You want to have a lighter density of what I call fuel, which is trees and bushes. And then the extended zone is beyond that. This is my friend Daniel Gorham. He's going to show you how the same house can ignite in 2 different scenarios.
So from start to finish, we're going to start with our ember generators, which we use to recreate a realistic ember exposure. Embers are those small burning and smoldering particles that may travel ahead of the fire front. And what we do with our generators is we create the realistic exposure, and in our wind tunnel, we're able to throw them at a building. And then we have a building that has 2 sides to it, a good side, which uses wildfire resistant construction, and what we're considering a typical building that we would see in a wildfire prone area. Exactly as we expected, that mulch on the ground there caught fire from the embers. The fire from the mulch burned up under this deck, and this whole deck was on fire. And so this fire on this deck caused flames right against the home. And then if we look there at the base of the door, it was actually the flames from this deck that burned through the bottom of the door. And on the inside of the house, we started to see smoke and flames. And so because this deck was a combustible material attached to the building, when the embers led to the ignition of this deck, we got flames inside of the building. Here we are on the wildfire resistant side of the house, where we had non-combustible siding, a 5-foot non-combustible zone and 6-inch gap. We had a metal gutter and multi-pane windows. And we see in comparison to the non-wildfire resistant side, this side had the same ember exposure. If you look here in the mulch, you can actually see some of the embers that had accumulated, but because they had no susceptible fuel to ignite, they just landed there and fizzled out. And here where we have ornamental vegetation, that again is susceptible to the embers, but because it's more than 5 feet away from the home, it didn't have enough energy to ignite, and it never led to a flame impact on the building.
So what we can see here is that one home may differ from another in almost imperceptible ways, but one home will absolutely survive. It's all about breaking the link. Fire fundamentally needs enough energy, of course, oxygen, to actually initiate this combustible reaction. And one of the key components, of course, is you need a fuel. So by breaking the link, by removing the fuel, removing the energy, we can actually stop the wildfire from progressing. And this is how fire science has dealt with fires in very large structures, and it equally applies in these smaller structures. We should also mention that the building codes are at play here, and they are changing and have been changing to adapt to the new scenarios. California's Chapter 7A sets standards for homes in these fire-prone zones. It has been enforced in various ways over the years, but you can expect to see greater enforcement. The key aspects of it are that it addresses the exterior walls and siding, roofing, including a Class A roof covering that we discussed before. Class A, by the way, should resist a brand for approximately 90 minutes. And also, over the period of 10 minutes, there should not be more than about 6 foot of horizontal flame spread when you have a 12-mile-per-hour wind. The vents and openings are critical, and they're addressed in different ways. You can use exotic intumescing vents, or you can just use a wire mesh. But the key is to prevent those embers from getting into the home and affecting those materials. Attachments are something else that is also addressed in this code. In terms of fire resistance and embodied carbon, I think you have to talk a little bit about that when you're talking about building resiliently. My colleagues here will definitely speak more to this, but I will say that fire resistance and carbon have had a traditional relationship. Things like concrete, steel, brick, and stone resist fire well, but carry a very high embodied carbon. Wood, of course, is low carbon, but in some forms, wood is maybe not as fire resistant. But what's interesting, again, is that you can make sure that wood is a fire resistant material if you apply it correctly. We spoke about mass timber as an example used in high-rise buildings, but also it can be used in low-rise buildings, CLT. These panels have enough thickness so that you have what's called a sacrificial layer that chars. The layer under it retains the strength. So it's all about smart material choices. Here we see a house by a local architect, Michael Kovac. This house is a house that recently was involved with the Palisades fire. It's been on the news, but he specifically designed it to withstand the fire. And some of the things that he was doing were dealing with defensible landscaping. He used elements like gravel, volcanic rock with fire-resistant succulents. He used non-combustible siding. He could have made a choice, like many do, to use combustible siding, but in his case, given the location of his structure, he wanted to go into a little extra care to make sure that he could resist a number of different fire spread mechanisms. Of course, a Class A fire-rated roof and high-performance windows. Windows are not necessarily weak points. They have an incredible ability to resist thermal, infrared radiation. The key is maintaining them intact during a fire. Tempered glazing is one of the best types of window to use for that. It was LEED Platinum certified. And what that reflects is a home that meets energy standards and has a certain inherent tightness. That same tightness can serve you extraordinarily well in a fire. Recycled and low impact construction, they actually were able to take down a house that was there and recycle many of the components. Passive design elements, again, insulated windows, green roof, and architectural innovation was another hallmark. So all of these things together were how he assembled his fire-resistant home. So in conclusion, it's about a layered defense. Resilience isn't just about the materials, but the materials are important. Any material can be resilient in a different way depending upon how you utilize it. There are both combustible and non-combustible paths for making something resilient. The maintenance is a consideration that is ongoing. Just like you have to consider the details, you have to consider how you maintain that home after the fact. I can point you to IBHS's Wildfire Prepared Home, NFPA Firewise, or other programs from nonprofit organizations that will teach you how to do this for your own home. So while the risk isn't going away, and we can argue that the risk, quote unquote, is increasing, if we work with materials in an intelligent way and think about what we're doing relative to the exposure, we can actually thrive in this kind of environment. Thank you.
Thank you, Nate. And as we pass our computer from a speaker to another, I wanted to just pause and mention we have heard the words embodied carbon. That refers to the carbon emissions, the carbon footprint of making materials, in opposition to operational carbon, which is the carbon footprint, the emissions of operating a building. So this is why we use this word embodied. You also mentioned tightness, which refers to air tightness, as we want to make sure to control how much air goes in and out of our houses as we care for how much energy we spend to heat and cool them. But let's talk about healthy materials now. What do we do about this, Alex?
So, as I said earlier, my entry into really taking a deep dive on materiality and the health of materiality was dealing with a water-damaged home. So, a different form of challenge, a different catastrophe to deal with. And it was only through the kind of the research that I was doing, starting with something as simple as the paper facing on a wall of gypboard. And some people might have just said, well, build out of fiberglass or think differently. But I was researching in the mold forums about the healthiest form of construction. And I heard a word that in all my years of practice, I'd never come across before, and that was hemp lime or hempcrete construction. And when I looked into it, it made a lot of sense on many different levels. What was interesting to me about it was the potential of basically a farm-to-table mentality in the world of construction. That here we were, driving up to Ojai on the weekends, or thinking about going to the co-op in Santa Monica and places like this. They're all about health, and to me, that became synonymous with Southern California and the lifestyle here, hiking and surfing. And so I saw this connection between natural materials and the potential to build out of natural materials as kind of an extension of the way that my own personal culture living here in Southern California was evolving. And when I started thinking about this, even more seriously, it was 2020, we were all home working remotely, and there was a webinar on healthy buildings. Two professors at Harvard who had been doing research on how to make buildings healthier and the business case for doing so. And I saw the potential here for changing the lens around resilience. COVID, obviously, a different type of issue that we had to deal with, and therefore resilient response. But also thinking about balancing resilience and a kind of regenerative type of thinking that was, again, part of what I was seeing in The Biggest Little Farm, in Kiss the Ground, and stories like this. And so at a certain point when I wanted to share this thinking, the contrast between a farm, whether that's, in this case, a hemp farm in Southern Colorado, or straw coming from Northern California, that this was in direct contrast to the type of materials that we were building with, in, say, commercial, institutional, and even residential construction. And I should also say that on a personal note, that when I had to go through a water-damaged house, I was working on roughly $50 million project in Southern California near Disneyland. And at the end of it, we were asked to gather the list of chemicals that were in the buildings for I think it's a Prop 65 warning. And I was thinking about how hard I was working during this time, and a building that beautiful in many ways, but that also had the potential, even from the level of regulation, say, had to disclose cancer-causing materials. So this is a contrast here in the photo between Cancer Alley in Louisiana, well-known, well-documented as a place that they're making chemicals. But that also happened here in Southern California, the Exide batteries, in where we live now in Tucson, Arizona, also chemicals, forever chemicals, that had permeated into the groundwater. When we left Los Angeles in May of 2021, there was also an opportunity to look at different places to live. And one was outside of Denver, and ultimately we ended up moving to Santa Fe. But we were then keenly aware of and attentive to the stories that were coming from the Marshall Fire back in 2021. And one of the things that was most striking to me was that homeowners were not allowed to return to their homes in many cases because it was too toxic to do so. And you could have a beautiful home, a place for your family, and yet when it burned, this was now unlivable in many ways. And so this is the reality that many homeowners in the Eaton fire and the Palisades are going through right now, and something that we all as a community are becoming more aware of as architects and professionals. And so for me, this opportunity to just pause and reflect is also one to think about moving from, say, an immediate response to the desire to rebuild to one where we can consider the potential for regenerative impact. That if we build in ways that are carbon sequestering, that are using more plant-based buildings, and that could be wood, straw, hemp, a variety of different materials, that those could be carbon sequestering, healthy, and fire resistant. So simple diagram to say that that's the research that I was doing. I wouldn't say I was focused specifically on fire resilience per se, but on resilience as a whole. And so this intersection between carbon sequestering to think about the larger issues at play, the larger environmental issues, non-toxic in terms of the chemical makeup of some of these, and resilience as a way to be able to deal with the changing world in which we live in. So when we ended up leaving LA and moving to Santa Fe, New Mexico, that was in the home of Architecture 2030 at Mazzaria and Company. And so when I presented this to the AIA Santa Fe, I thought, well, let me talk to them about embodied carbon and make the case for hemp lime construction at that point, specifically in terms of embodied carbon. And how, as codes continue to get more stringent, what we're really talking about moving beyond operational carbon, in your case, maybe your utility bill on a more immediate level, moving towards the embodied carbon, the materials themselves. And so this is obviously architectural research, very much diving into codes and policy, ways to think about how we as architects and designers and humans can have agency to be able to change the laws. I know that there are petitions out now for people to consider the possibility of rebuilding with adobe, rebuilding with straw bale, materials that were presented to the California Building Standards Commission. I was one of the many people who was on that call several months ago to allow the California Building Standards Commission to consider this. They didn't at that time, but I'm hoping now at this point they will take this into greater consideration. Another piece of this is to be able to talk to potential homeowners, to the larger culture, and look at some of these maybe non-architectural examples of ways to talk about materiality. If we talk about organic food, we go into, say, a supermarket and we see an organic banana versus an inorganic banana. At this point, I think many of us would choose the organic banana if there's not much of a big difference in price. I don't think we have the same level of consumer awareness or client awareness, cultural awareness of what that means yet in the built environment. But I feel like that this is a moment at which we're starting to make those changes and start to learn. For some people who may have seen Dark Waters on the streaming, talking about forever chemicals and some of the impacts of that. So when I was proposing looking at hemp lime construction and natural materials overall, what was interesting to me was that the ways in which people were building were similar to the advanced building assemblies, basically putting insulation on the exterior, which from a certain perspective, preventing heat transfer. Also increases insulation value, but it also, in moments like this, prevents heat transfer into a building. And so similarity in my mind between two really quite radically different ways of building had similarities in other ways. And so you can see that on the example, a simple image on the right, that there is material on the exterior. It's basically encasing the wood frame, and that's basically protecting the wood assembly from actually ever burning. So you can see we talked a little about embodied carbon before, and we're talking about materiality and toxicity. If you look at the top part of the central graph, all the petrochemical-based products have higher embodied carbon, and they have a chemistry that we're trying to move away from. Whereas the materials at the bottom, dense packed cellulose, cork, hempcrete, straw bale, all high embodied carbon and all natural materials. I think for a lot of us, there's a kind of issue of perception, and Nate spoke a little bit to this about wood, mass timber, the difference between, say, what we would call in the architectural world type 5 construction or 2x4s and heavier timber. Similar thing happens when we look at either straw bale or hemp lime or other forms of natural building, and that is that yes, they can char on the outside, but actually that they can perform 30 minutes, 60 minutes, 2 hours in some cases, depending on the exterior finish. And so the perception that a natural material, which many cases would burn on its own, is different when it's built in these ways. And I think that's an important takeaway for me, is that we're trying to wrap our heads around how do we rebuild in a more resilient way. And we're also having to kind of uncover some of these perceptual shifts about how we think about these materials. So these are just a few, this is typically shared as a hemp or hemp lime construction materials presentation, but I've also added in wool insulation, cork. There's a company that's collaborated with the University of Colorado, Prometheus Materials, that's looking at low carbon concrete made out of algae. And so I think this is a very interesting time for us all to think, obviously the immediate response, but the larger issue of moving towards more natural materials overall. Thank you very much.
Thank you, Alex.
So we were looking really at this moment we are in back in 2022. The project was part of the Department of Energy's Solar Decathlon. And that January of 2022, we decided that we were going to enter it. And then in April, we won the first phase of it. And then we decided that we had already decided that it was going to be a 3D printed project on multiple levels. We were really looking at the housing crisis, homelessness, and climate change. You can see that slide to the right, and that was part of our competition entry back in 2022. So we're really looking forward, and the project was, the moniker for the project was Solar Futures Residence. And we looked at it in terms of how we might go through the design process and build something that could withstand climate change, not just only for fires as well. And so this is also a reason for building with concrete, even though as we've talked about, it's not the best in terms of its embodied carbon footprint. These are some of the students who took part in that competition. And we were doing a lot of investigations and experiments in terms of how this could come together. We had to, during that time, we had to also work a lot with the weather. We had a couple of atmospheric storms come our way, and we had to then really deal with climate change firsthand as well. A lot of learning. These students are now graduated. They're young and emerging professionals doing enormously significant work right now. So why 3D printing? As I mentioned, we were looking at the housing crisis as well. So it was a methodology to build faster and smarter and bring more supply into the Los Angeles housing stock, which, as we all know, is quite low right now. So that was the reason. And for 3D printed as a material, it was concrete. There's quite a few advantages of building with concrete. The project had many lines of defense. So starting with the roof assembly, we have a metal roof. We have 9 inches of a rock wool or a mineral wool, which is also fire retardant. On the building envelope, so when you think about designing for resilience, you think of the envelope of the building, so roof and walls. And so we've got like a 10-inch wall here of concrete. And then we've got, because we love the materiality of wood, the warmth of wood, we chose it very strategically to complement the concrete. And you will see some slides where you do see the touches of wood, and above the concrete in the wooden stud wall, we also have the fire retardant insulation. So it's not only just sort of allowing for a microclimate in terms of comfort and thermal resistance, meaning it keeps the interior quite cool when it's hot outside, because concrete also has a very high thermal mass. So there's that benefit as well. These are sort of the construction slides that of the time that we were building this. That's kind of what it looks like right now. You can see the roof. It's also net zero, which means that the energy that's produced by the solar panels, the PV, is sufficient for the user, and it sort of zeroes it out. So it's a net zero house. That was part of the mandate from the competition as well. We also did, we had a lot of other strategies in terms of water conservation. So in terms of what we refer to in industry as passive strategies, having a lot of natural light, having a lot of natural ventilation was important to us. So the slopes of the roof really follow the path of the sun. So a lot of analysis in terms of where to place the windows, which windows are operable to get the maximum cross ventilation going across, and so you're not turning your AC on. These are sort of considered passive strategies. So a lot of analysis went into the slopes of the roof and really kind of following the path of the sun in terms of the maximum solar exposure on the south and the west of that roof plane. Now, again, to do that, and sort of the curvature of the building was seamlessly done because of the technology. So something that would cost a lot of money in traditional stick-built building methodologies, the printer just sort of seamlessly does the form that you ask it to do, pretty much. And you can see that in the facade, in the front, and you can also see it on the interior, on the opposite side. The roofs also act as rainwater harvesting strategies. So we've got a rain barrel. You can see it in the middle side towards the left, there's sort of protruding the green barrel there. So the south west roof is capturing the rainwater in a rain barrel, and the eastern side is capturing that in a planter. So these were kind of done as design strategies, again, looking to drought-resistant plantings and things like that. But also it became mandatory for us to get to CFO, meaning certificate of occupancy by the city. We've learned a little bit in terms of how we might have not had to do that, because we really wanted something to start living in it. And so that took a little bit longer because it became part of the permitting process. On the windows are looking north, so you get a lot of early morning sun, which is quite beautiful, and you got some windows across each other, taking that air across and creating a lot of ventilation. So those are some of the passive strategies. This is sort of integrated systems that I've just spoken to you about. It also has a first use case actually for Los Angeles, where we're recycling gray water from the shower. It goes into toilet flushing, and you can use that system in your single family residences now because we've done it as part of the city of LA. So this is kind of looking at it through a holistic lens, looking at it through a systems thinking lens, and looking at all of the things that can come together to make the house as efficient and as effective as possible. And thereby mitigating for energy use, for water use, and of course for the elements, and specifically for fire. This is kind of the installation that I was talking to you about. So you can see it's sort of not burning. This is the vendor we use is Rockwool, but there's other vendors that do the mineral wool that doesn't sort of burn. And so you got that in the roof in terms of 9 inches, and we call it also in terms of thermal resistance, sort of a R38, which is very high for keeping that microclimate in place. So concrete, yeah, we've talked a bit about concrete and how bad it can be. But just as a fun fact, it's the second most used material in the world. So it's kind of not going anywhere. Even if we try to sort of say, hey, like, don't build with concrete, there are other parts, especially in the global south, where it's ubiquitous. So how do we make a material that's prevalent better? So this became part of our research, my own personal research as well. And what we did was we worked with a local plant, and this is still available for anyone to leverage, is that we were doing carbon sequestration in the concrete. That was one strategy that we used. And wood does that naturally. It sequesters carbon naturally. It absorbs CO2, and then through photosynthesis and so on, it emits oxygen. But here we had to do it artificially, so the plant had the infrastructure to do that. And what that does is it's embedding the CO2 while it's being mixed. So we're sequestering it permanently. And when it gets recycled, the concrete is a recyclable material. At the end of its life, it's EOL. You can recycle it. It doesn't emit the CO2. It just keeps it there. The second thing we did was, so the culprit in concrete being sort of this bad thing for the environment is the cement. And it's in the manufacturing process of the cement that there's a lot of CO2. So one way of doing that is to supplement the cement with something else, and we call that SCMs, or supplementary cementitious materials. And in this instance, we reduce the cement content by 40% by substituting it with something called fly ash. Now, fly ash is a byproduct of coal manufacturing, and it is sort of getting lower because we phased out coal. Obviously, that could change anytime soon. So in this instance, that is what we use. But there are other things like lime that can be used to supplement the cement and reduce that cement content, thereby making the concrete's carbon footprint lower as well. So there are ways to make the concrete greener and more sustainable and more better, and that's become part of my personal research as well. So you can see we sent it for testing. One of the sort of the side findings was that because of the CO2 sequestration, the strength of the concrete became really high. So much so that the plant thought they did something wrong, and they sent it a second time just as part of their due diligence to double check that the strengths were coming out as what they were coming out at the 7 and the 14-day mark. So these are some of the things that we did for concrete, because I do believe, it's not just fire, but if you look at any climate disaster across the country, whether it's a hurricane, whether it's a tornado, it's just sort of, the wooden houses end up being sort of these matchboxes, right? Just smashed up in a pile of wood. So we have to build better and really smarter in terms of building for climate change. It's kind of the student team in the house. I believe that's it. Thank you.
Thank you, Kishani. And as a little editing note, we know that there's a lot of innovation here in the space of concrete. There's a lot of US innovation there that leads to extremely low carbon footprint, right? So there's actually a lot of responsibility from the fantastic, work doing by the concrete industry, the cement industry, and so we're seeing things shift, and so possibly, those statements might change and evolve, and this is a very dynamic landscape. So next we have Herwig, who will also bring the holistic vision of the architect, similarly to Kishani and previous speakers, merging all those considerations of fire designs and resiliency into your project. Herwig.
Yeah, thank you. So I'm going to talk a little bit about technology in this context, and also then specifically about ceramics or terracotta as a building material that has multiple advantages. Again, kind of like this chart, which was mentioned before already. There's different points of ignition to materials, and there's not just direct. Obviously, in the Eaton fire and also in the Palisades fire, we had extreme high wind speeds, and so amber was a huge issue, flying amber and ignition through that. But previous fires, where the wind wasn't that much of an issue. I remember the Malibu fire. We had very high temperatures in close proximity to the building, and so even if you do have a kind of low fuel around the house, you can get up to very, very high temperature that lasts for a very long time. So what can happen, obviously, in that scenario is that stuff inside the house starts igniting. Paper has a flash point of 451, for example, and so different material ignite at kind of different temperatures, as this table is showing. And building out of concrete or combustible materials, as was mentioned before, obviously has its clear advantages here. Ceramic tiles, this is mostly why I'm showing this slide here, is 2000 degree Fahrenheit, so it's a very call it fire resilient material. It's also a natural material. It's some clay is obviously something that exists everywhere, something that can be locally sourced, doesn't have to be transported. And it's actually, especially in Los Angeles, quite a lot of examples of terracotta buildings in downtown Los Angeles if you drive around. There was a period of time where that was heavily used, and I think it had its renaissance in the last 5 to 10 years as a material come back, and I think it's specifically relevant in the context of fires and fire resiliency. This was already mentioned. Obviously, there's a series of passive strategies and active strategies and systems. So I'm not going to spend too much time on the passive strategies because they've already mentioned. A lot of it has to do with landscaping, material choices, but then there's also active systems that have to do with high flow sprinklers, fire shutters, and foam as a way how to deal with these. So this is a diagram similar to the one that Nate was showing in terms of like what type of vegetation at what distances from the home to reduce fuel. We're going to show a few projects after this where it's also extremely relevant to have a body of water on the site, and that can be achieved through different things. If you don't have a pool, you mentioned gray water collection that can go into a tank. So that's, in case you lose, which happened during these fires a lot. It's, fire department obviously was using most of the water available. And so if you have a water source on site that is either in form of a pool or in form of an underwater tank, is obviously very important. So it gives you some sort of independence from the system. This is a list of fire retardant landscape plantings. So these are all native California plants, a lot of succulents. Live oak is actually a great tree to have next to your house, but there's also a series of other plants that are quite beautiful. And often the stigma is a little bit like, oh, I can't have any landscape around my house because of the fire fuel, but that's actually not true. It depends on what kind of plants they are. So I think to be aware of what talk with a landscape architect about what kind of planting is fire resilient or has low capacity for being fuel is just a smarter way of creating landscapes around your home that can be both beautiful and efficient in terms of like fire resiliency. The other thing that often comes up is as a design issue is that glass, so this is California. Obviously there's a long history of modernist buildings, mid-century, has a lot of glass in it. And how do you deal with that? Obviously this is a big exposure in case of fire. And so the other thing is that these overhangs, large overhangs, are on the one hand fantastic because they provide shade to the building and a comfortable outdoor kind of environment, but they also, in case of fire, can become a trap for amber to collect. So we did this study where we looked at fire shutters that can be installed in those kind of overhangs. And also create some sort of a buffer between that and the glazing. We're going to show this in animation in a second here. So, as mentioned, a water collection, especially gray water collection in form of rainwater, but also in terms of like your daily use water, could be filtered and stored locally. So you have a subterranean water tank or some sort of a body on site that can be deployed in case there's a fire. Obviously, there's different versions of this, and it's we notice on an institutional level, like At.The, of course, has a system like this installed, but it can also be in a much smaller scale be installed on a residential scale. So that's one line of defense, is to sprinkle the outside of the project. The other one is, I think this is the movie, is to have these shutters. And as I mentioned, two issues from a design point of view. You do want to have transparency, obviously, in this climate and environment, but you also, by installing these shutters, it allows you to basically eliminate the overhang, so the fire actually has less areas where they can catch. And then when the shutters are down, there is a airspace between the glass and the shutters, which provides additional protection. So this is what this looks like in real life. They are often triggered by sensors, right? So when we sense that the fire is close, these shutters come down and seal off the project. In terms of like what these shutters look like, they're a combination out of panels that are insulated panels, like usually 1 or 2 inches thick, that roll up into a box that you can hide in the soffit of your project. Like a detail of what they look like. There's different kind of materials that are used to produce these kind of panels. Now, I think one big advantage of that is that you, so this is 2200 degree Fahrenheit at the fire at the house at the shutter, but the airspace actually between the shutter and the glazing is quite important because that provides a buffer, so that can get hot without heating up the house, right? So it's basically an air buffer that provides some cooling before it enters the house. Obviously, it's all a matter of time. So if you have this situation for a few hours versus for 12 hours or longer, that becomes increasingly harder and problematic. So as a kind of secondary system to that that exists, of course, that's also quite expensive, is if there's a breach in the shutters, then there's a chemical foam deployed on the inside that could put out the fire. This is a study we did for a house in Malibu that we designed after the fires, and basically looked at a variety of different systems working together. So the one already mentioned is a subterranean water tank and the sprinkling, which would be defense line number one. The second one is to have fire shutters that close and provide almost like a stealth kind of shell that has very little areas for the fire to catch, and provides this buffer between the quote-unquote balcony and the enclosure of the building. And if the interior temperatures here reach 150 degrees Fahrenheit or higher, we're looking into a heat exchanging system that would reduce the amount of heat that exists in these air buffer spaces. And then, as I said, phase 4, which is kind of extreme, is to have that chemical foam that can put out fire. So these are different measures, not all of which will always make sense. Sometimes it's a combination out of one or two or multiple of these kind of like measures. And those are in addition, obviously, to working with materiality. This is more of a mechanical way of providing protection for your home. Okay, so the second part of this is terracotta, as I mentioned already, and this for a variety of reasons obviously has a high fire resiliency as a material. It also has lots of design opportunity in terms of like texture and color that you can choose from. And it's a really sustainable material in terms of it's locally sourced, and that's ancient old material, as you know. So obviously there's some examples of contemporary use of this material, and we at SCI-Arc have done several research projects with students. This is students' projects from a couple of years ago after the Malibu fire, where they designed a fire-resistant animal shelter, which the Malibu fire was a big issue as well. Like there was no place for the animals to go. And they're looking at terracotta or tile as a way how to provide that protective barn, if you want. And we'll show in a second here what that looks like. So the students designed this more of this kind of stealth project, if you want. So it's a geometry that is less prone to catch fire. And then they designed a build-up for it, and then build a prototype of it. So this is the kind of mock-up that the students worked on and designed. It's a back-ventilated facade that's insulated. As was mentioned before, there's a range of different insulation material that are sustainable, that can be used for that are quite effective. And so it's important that to have a multi-layer system. So it's not a single layer. There's the terracotta, obviously, is the most outer layer. And then there's a ventilated area, and then this insulated area. This is some images from our robotics lab where the students worked with the robots to produce these tiles. Then obviously the tiles get fired, so the clay is initially wet, you let it dry. Then there's two kinds of firing processes. So the bisque firing, where you heat up the material up to 1,000 degrees, which makes it porous. No longer is it, you can modify it. And then there's a second firing up to over 2,000 degrees Fahrenheit, in which you glaze the material at, you apply glazes to it, and that produces a waterproof, resilient, very resilient surface. And that's, in this case, these are three-dimensionally shaped tiles. And then they are designed so that they can be assembled, like you see here, in a mortar bed or with attachment clips. And there's obviously a lot of possibilities here in terms of color, texture, what this can look like, and produces this fire-resilient envelope in this case. Okay. So that's the kind of finished markup that the students designed and then built. I also wanted to show one other project that looks into incorporating, not just providing this is less about providing a fire-resilient screen, but it's integrating algae as a way to produce energy and have a low carbon exterior facade. So in this case, it is terracotta combined with microtubing that you see embedded here in the terracotta that basically pumps algae through. The system uses the sunlight to basically take the carbon out of the air, the pollutants out of the air. So these are some examples for that. And I believe I have a video of this where we can see it working. Oh yeah, so this is a short video. Again, this is a student project, research project that deals with retroactively putting it on existing buildings as a sunscreen in this case. And then this is the microtubing with the algae that gets integrated in the terracotta. This is some pictures of the production of it. And that is used for a variety of things. So the algae can be harvested, also used for food production, but also, as I mentioned, this is also produces a low amount of energy, and that can be used for the building as well. So this is, again, the process of firing the final product and then the assembly of it. And this is basically the microtubing. You can see how the algae gets pumped here through these small tubes and produces the kind of small amount of energy. So, it's just both, I guess, just in summary, there's both in terms of research, a lot of work being done here at school with fire-resilient materials, terracotta specifically, and robotic fabrication. And on the other hand, I think we wanted to show also that there's a series of technologies out there that you can use or integrate into residential construction that are more mechanical ways of helping to provide a fire-resilient enclosure. Thank you.
Thank you, Herwig. Definitely a lot of innovation by our students and beyond in Woodbury and everywhere where you guys present your work and inspire them. So as we transition from this ultra quick presentations into our panel, I'm going to turn it to our panelists to discuss a few, takeaways and thoughts that we will share with their attendants. I'm taking notes that there are dozens of people online and possibly more when people will be looking at this in the future. So a reminder to send your questions in a Q&A and also address them to us at SCI-Arc, and we will pass them around, collect them, and this will inform the research that we turn back to the public again. So a few questions, and I know we have a few starting questions, and I'm sure we're going to have a lot of organic follow-ups together. But as a start, I wanted to just talk about bringing it back to where we started, talking about the fire event and what we witnessed and how we can prepare for rebuilding resilience. So, Nate, you've talked about prior fires. We've heard about Paradise, Thomas Fire, and further down the line. What did we learn about this specific fire with relation to those three propagation you talked about, the direct flame contact, the embers, and the heat. And what was the most prevalent here in Eaton? I mean, I'm sure there's a lot of forensics going on, so I'm sure this is going to be partial information. But what did we learn specifically about this mechanism and how they would inform the design of the homes moving forward?
Great question. Of course, we're still learning about the Los Angeles fires. Certainly in the Marshall Fire, which what we know from satellite photographs right now is that the Eaton fire, Palisades fire, spread in much the same way. There were some key differences, but whereas the Marshall Fire, which we heard about earlier today, that fire was largely driven by embers. And then it was enhanced by structure-to-structure ignition, which is a function of that radiative heat transfer. When you have a direct view factor, and part of what fire produces besides the light, of course, is the thermal radiation. But as it does so, it heats up the air, changes the density of the air, and when you combine that with winds, we certainly had Santa Ana winds that were, I won't say unprecedented, but they were severe, between 80 and 100 miles per hour gusts. And when you have a buoyant plume that's heating and rising, it goes into the air, it carries these embers, very large embers, the size of everything from a walnut to tennis balls, that get lofted into the air for hundreds, thousands of feet, and then they drop, because as the plume cools, its ability to carry anything of significant mass also drops. Think of it like a hot air balloon. And the hot air balloon, you fill up and you let it cool, eventually it'll come down. You can carry a lot of weight with a buoyant plume. So the satellite photos that we saw of the Eaton fire literally show hundreds of simultaneous ignitions from embers on the rooftops and the structures of these homes. Then you have a secondary effect of a home ignites, and proximity to the adjacent structures is, in some cases, less than 14 feet. And that radiation is significant. It's, certainly between 8 to 14 feet is a very different scenario than from, say, 14 to 30 feet. The safe distance in a structure in terms of thermal radiation, where you would not expect an ignition due to radiation, is about, call it 59 feet. So you really need a lot of separation. And the fact of the matter is, we don't have those separations between our homes, not in our cities. And that is why the wildland-urban interface is so significant. We don't have the separations to just naturally prevent what's going to happen. And certain products like ceramics, I use ceramics on my home. For portions, I use a combination of ceramics with pre-burned wood, shizugiban, together with concrete, which, I understand it's a material that has a high embodied carbon, but I was trying to respond to the facts that I live in a dense neighborhood. So long and the short of it is, these fires, the way they spread through the communities is not unknown. And in Palisades, of course, the winds were driving the fires, in a very distinctive direction. It's almost unusual that a fire would burn downhill in a sense. That doesn't seem intuitive, that it burns downhill. Most of the time we see fires burn rapidly uphill. And that's because as the fire burns, it preheats the fuel in front of it, which makes it easier to ignite, and then it runs up the hill. That's what we see. But what we saw in the Palisades fire was a downhill fire spread, which obviously happens, but it shows that wind was a dominant factor there. And the wind carrying the embers, lighting thousands of spot fires ahead of the fire front itself. And so those factors it's like dropping 1,000 Molotov cocktails on a community all at once. And in that case, it almost doesn't matter, what water supply you have if you have thousands of simultaneous fires. And that's why materials become a primary line of defense. If you don't actually ignite the building, or you have a very difficult scenario to ignite the building, that's an excellent defense. It's not to say that active systems like sprinkler systems are not important. I personally believe they're critically important, and it's been said by many who witness how fires attack these communities that a quote I'm fond of is, "A wet house doesn't burn." And that's true. There's fires like the Lake Ham fire where they used sprinklers, exterior sprinklers in a number of the homes. All of the homes that had those exterior sprinklers survived, and virtually all of the homes that did not survive that particular fire. So it is notable that if you have the water supply, that those sprinklers are extremely helpful. But oftentimes our water supply is compromised because we simply don't have the available flow when you have multiple fires in a community. We design our water supply system for one or a few homes that could be ignited simultaneously, not for dozens and hundreds. So those are kind of the things that we're thinking about with those recent fires. And they're things we've seen in the past, but unfortunately, we'll probably see it again in certain communities unless we start to address this.
I just wanted to take a moment to reflect on the response you gave us, right? It's a chain reaction. So as you told us, it starts, or it's primarily, at least for the Eaton fire, it was primarily impacted by the embers, right? I'm not saying it's the same, but I've heard anecdotal, maybe isolated cases talking about previous fires. For instance, I was in this fantastic passive house fire resilience webinar just a couple of days ago, and they had, I'm blanking, this fire in Colorado, Marshall fire. Professionals quoting, numbers of fire destruction, related to embers, saying that between 60 and 90% of this damage was directly linked to the embers. Now, it's a chain reaction, we understand that, but what could homeowners do to limit the embers, this first part, into the design of their systems? You and I, in preparation for this session, we talked about gutters, we talked about mulch and this kind of thing. Would you like to expand on that aspect, the first barrier of defense?
Sure. So embers are ignition points. They have sufficient energy to ignite a fuel. That's all you need to know about them. So the question then is, where do they go? Embers accumulate on first roofs. They will fly into any openings into the house through the eaves. They can land in gutters, and if you have debris or other materials, plant material in the gutter that's dry, that can ignite. So it's the term we use is stagnation points. It's like, where do the embers go? And this is why, for example, wildfire standards such as NFPA 1140, they have recommendations to maintain the bottom 6 inches of a structure as non-combustible, even if it's a combustible structure. It's because as you get the embers hitting the structure, some land on the roof, and that's where you have your Class A roof come in handy. Class A roof it's designed to have an ember the size of, it's 12 inches by 12 inches by, I believe it's 2 1/4 to 2 3/4 inches. They light it on fire in the test, and they watch what happens for 90 minutes. And if it does not burn through that particular roof assembly, along with the flame spread that I mentioned earlier, it's Class A. That's your Class A roof. these embers that we saw in the recent fires, again, comparable size in some cases, not quite a foot, but in terms of their overall ability to transfer heat through the structure, they had a similar effect. So it's important to watch your roofing materials especially. Embers are notorious for getting into eaves, into attic spaces, any combustible concealed space, basically. And even in a sprinklered home, many times our standards don't mandate sprinklers in the attic. They get up into the attic through vents, unprotected vents. The same vents that we rely on to exchange air are the way that embers will get into those spaces, and then they sit and they ignite the inside of the building, the concealed spaces where you don't have protection. Beyond that, embers, as you saw in the video, will accumulate, maybe in the landscape right around the house. And the ember is the kindling. It lights the larger fuel item, and then that lights the structure on fire. So it's about maintaining an ignition-resistant or non-flammable enclosure. That's the key. It's not complicated, but it's difficult in practice to implement. It's difficult to maintain the plants around your homes. We have thousands of homes with wood fences attached, but yet that's one of the number one ways that a wildfire will ignite the entire structure, is it'll survive the embers, but the fence lights, and then the fence has enough energy to ignite the house. It's strictly a matter of time to the energy exposure that results in ignition. And the reason why we look for ignition resistant or non-combustible materials is because they have the sufficient capability to resist that energy transfer long enough to prevent the oxidation reaction, to prevent fire. And that's what we try to achieve.
So wood fence abutting the house, decks. People should be careful about what wood products, thermally modified woods, or possibly substituting those in to metals for fences, things alike.
Yeah, there are lots of wood options, and of course, hempcrete. Hempcrete is effectively, it's not flammable. It has a flame spread of 0. Other types of hemp woods are nominally Class A. Even when you have a material that's combustible, what do you do to enhance that fire resistance? Well, we have a long tradition of stucco, for example, and it's a beautiful material. Or you could go with concrete, something that is also a beautiful material. And ceramics. One of the most beautiful features of the home that we recently built was a ceramic wall. That it wasn't as beautiful as what you showed, but we were going for a certain less beautiful aesthetic, perhaps. But it came out beautiful, and it protects amazingly well. It's something that we just have to think about on a case-by-case basis.
As long as we watch out for the gaps, right? We saw together as we were preparing the CAL FIRE, advising people to close gaps as much as possible between pieces of fire-resistant materials. The gaps could be a weak link as well.
Yes, and this is why thermally efficient homes, energy efficient homes, are prone to be more successful during the wildfire event, because they are inherently designed to be tight. When we build a house, there are all kinds of cracks and gaps that form over time as well. So this is where I had mentioned maintenance. It's great to have something that's pieced together, but you have to be careful to allow for flexibility in the future and to really watch the joints in any structure. It's kind of like, if you make it waterproof, you're doing a really good thing. If you make it airproof, also even better in a sense. So the more tightly you can construct your building, the better it will resist a wildfire. That's probably a very solid relationship, even though the data on that may be limited.
Mhm. This is maybe a nice segue to bring Alex into this exchange, because you have knowledge of passive house design and materials, biomaterials, the fire resistance of hemp lime materials is something that I was surprised myself. Even in France, we have those 3 little pigs, and we think that straw is gonna. No, straw has a 2-hour rating. Hemp insulation has a 2-hour rating, and so. Although I'm not a fire expert myself, Irsay, would you like to bring into this conversation the passive house airtightness and the biomaterials and the resistance to fire?
Yeah, I actually wanted to ask Nate the definition, the difference between airtight and smoke tight, because I've seen a lot of the conversations online about in the passive house community talking about smoke tight buildings. And in my brain, I wanted to make those connections similar as Nate's making right now, that if we solve for one thing, in many cases, we are also solving for another thing. But in this case, I didn't actually know what the definition of smoke tight was, or what the difference, again, smoke tight versus airtight.
Yeah, that's a great question. So a lot of the design work I've done is on tall buildings. And one of the things we have to do in a tall building is, because you may be thousands of feet in the air, you want to make sure that a fire on the 40th floor doesn't affect you on the 80th floor. And the main mechanism by which smoke, and fire spreads through those buildings is through building construction, through gaps. So we have to design the smoke zones, which are comprising typically floors, to be smoke tight. Smoke tight is designed, essentially, it's something that is designed to only allow a specific amount of air or smoke. In terms of what's happening in a fire, it's effectively the same as air, smoke. The particulate that makes it through the building it's basically so small that it might as well be air. You're not dealing with ash. You have other things like carbon monoxide. There's a famous fire that happened at the MGM Grand, where the fire was on the first floor, and there were dozens of people killed, and they were all on the upper floors of that high rise. The fire never made it past the first floor, but what got to them were all the products of that fire as they went up through the building through not smoke tight construction. So your point is taken, though. It's like, if you can prevent smoke from penetrating through the building, it's also going to mean that your post-fire cleanup is going to be dramatically better as well. And you can do that through passive construction, which has it's determined by what's called leakage factors. So you just construct it so that it doesn't have it doesn't exceed a threshold of leakage per square foot. Very tiny numbers. These are small decimals or tiny fractions. And at the end of the day, that's deemed to be smoke tight if it doesn't allow more than that certain quantity through per square foot. You can also supplement it, by the way, with active systems, even in smoke. We do it all the time. In fact, in high-rise, it's called a pressurization system or a depressurization. It's really not something you even necessarily feel. If you were to breathe on your hand, just blow on your hand like that, that's all you need to actually prevent smoke from infiltrating into or past a smoke barrier with adequate leakage. So it's all over the place, but you bring up this point that something that's tight it's going to actually prevent that smoke from getting in. And of course, if it prevents smoke from getting in, you're not going to get embers or ashes, which are much larger.
It's also, I think, in the houses that do survive, we have done renovation of houses that had a fire inside the house, and you end up essentially taking down everything, right? Because the smoke and the smell is everywhere. So you have to take off all the plaster, all the chipboard. Sometimes you have to get into the studs, etc. It's very hard to get rid of. And so to, even the houses that do survive to have a smoke tight system, so it's very beneficial, not just for the embers, but also for the, as you said, for the post cleanup, or even if the house survives, then that's obviously a huge benefit. I mean, I also think that, we have increasingly in California issues with water, there's less rain, etc. And I think to be both for the building codes but I also think for these structures that are being rebuilt. I mean, you showed you have a gray water system, it's a great way to actually either maintain a body of water on the property and be independent of the grid. Often that's used just for irrigation of the landscape around it, but I think it's also could be a great resource for longer time storage to have a body of water to provide things like wetting down or sprinkling your building, etc. So I think as we are moving forward, and the sparsity of water is on multiple levels, not only just to preserve water and spend less and collect the one we have, but also use that as a kind of measure, possibly.
Yeah, I would echo that. The body of water on the property is critically important, not just during the fire, but sometimes even before the fire. So people will use if you happen to have a swimming pool, some underground tank, you can use those before the fire to effectively humidify your property. And a wet property is much less likely to burn. There's a certain humidity threshold at which fuels dry out very quickly. And, when you're in an environment where it rains regularly, these trees, we don't get these wildfires, all around the country. And that's because largely they have humidity levels maintained consistently higher than what we have in Southern California. So if you have a fire coming and it's fire season, you could use some of that water perhaps, once you get through this notion of how to take water from your pool and spray it on your land. You could pre-wet your land, and then that buys you hours. And then you can add to that certain products like gels that are mixed with water, and they retain the moisture for even longer. So you can have 24 hours, for example, perhaps where your immediate surroundings are wet or humidified, and it makes it much, much harder for a fire to spread. It's no accident that we very rarely get large wildfires in certain parts of the country, and that's really comes down to humidity.
Interesting. I was having a conversation with an MD/architect about architecture and health.
What's MD?
Medical doctor, sorry, in Vermont, and we were talking about how the relative humidity of the indoor air quality was paramount for healthy indoor, for occupants. And here we are talking about it. So I love always to think about the kind of macro levels of engagement.
Would you like to go back to the hemp?
To answer the question?
Yeah.
Not to deflect, but to come back to the question. Yeah, for me, I think when I think about it, it's not simply hemp or straw or cork, although a lot of these times the materials themselves do have, say, high silica content, which prevents, or naturally leads to creating a fire-resistant material, but that also that the way these are used are basically biocomposites. So if we take, the specific material itself, out of the equation and think about biomaterial or biomass mixed with lime, which is a material that's been used in vernacular architecture all around the world as a fire-resistive exterior material, then you say, well, naturally it makes sense that we're bringing back some of the traditional knowledge or vernacular knowledge about how to build in different environments, and we connect it with ways that we're building in contemporary ways now, then to me that aligns. And if we take that thinking and start investigating other material systems, we kind of fertile ground for research.
And what do we know about the fact that the air was contaminated? Like I remember just walking around like North LA, and really feeling a bit sick, and there's people in Highland Park that had to leave the neighborhood, these kind of things. And obviously with, unparalleled, without any comparison to what happened to At.The. I just want to think about the future of the soil that's there, right? And so I'm not so sure about the Eaton fire, but you mentioned the Marshall fire, or, significant thicknesses of soil where kids are going to play, you're going to walk barefoot. These things, the food you may want to grow there, or just as chemicals surrounding your home after the event of a fire. How do we tie back to our decision making in the home we inhabit? Because you mentioned, the health of materials, living in a house and choosing your materials during the living. But what about remediation of soils and how toxic those soils are? And shall we have a few words on this?
Yeah, I think, for those of us who've had to sign releases, a new lease, there will often be, for an older house, I remember the last lease we had in Santa Monica, about lead in the soil. So we don't use lead in the soil, or lead in paint anymore, but because it was used in the previous era, there are still trace amounts of it, and there are things that we need to pay attention to, and for legal purposes now we need to sign releases. I think, similarly, if we think about, say, vinyl siding or other petrochemical-based products that are releasing phthalates or dioxins or materials that we're not used to measuring in terms of air quality. If you go into some of the air quality maps, there's a great one, IQ Air, they look at primarily particulate matter, like PM 2.5, things that are coming from diesel exhaust. I've done a little bit of research. I haven't done a deep dive, but I have yet to see air quality data that includes some of these other chemicals that are harmful for us. We know from indoor air quality, we talk generally about VOCs.
Can you spell out for our audience?
Volatile organic compounds. So if we think about new carpet smell or new car smell, those are volatile organic compounds. Those are chemicals that are not good for our health, and yet we're learning to measure more and more detail. And so there was a post from the Parsons Healthy Materials Lab a few months ago that had done a post-occupancy study on one of these hemp lime houses in Pennsylvania, and they were able to show 400% less, I think it was benzene, in the indoor air quality. Typically not something we measure. And so as we're trying to assess what the impact of these fires is, in many ways we don't have the tools deployed to measure these, unless, Nate, correct me if I'm wrong, but...
No, I'm not here to correct you on anything there. I think that it's not an unfair generalization to say that materials that either A, don't burn, or B, are more what we would call natural materials. Tremendous difference in terms of the toxicity after the fire. Natural fires, natural wildfires do not produce the same types of toxicity effects. Now, it's not to say that there aren't significant concerns in the midst of the fire, but the synthetics, the conventional synthetics, plastics, hydrocarbon-based materials are incredibly nasty, and even more so in the context of a large burn area. So those are the types of things, when we talk about resilience, I think it's important to make that connection to, these are oftentimes things we don't want around our kids in any context, yet we move into a house that has very little consideration for, or oftentimes had very little consideration for these materials in the actual construction of the house. And it's like this toxic container waiting to explode during a fire event. So some of the materials we've heard about today are interesting to me, because I can say my close friends were worried about the very thing you were mentioning, is my 3-year-old little girl is going to play in this park next to the house that's 1 block from where the fires were. I don't know if I can live with myself and let her play there. So you have to remove the 6 to 12 inches of soil and deal with, the toxic materials. But wouldn't it be great if we could just have something that's hundreds and hundreds of times less toxic to begin with?
Mm-hmm. And we've seen studies where this is not only linked to cancers, you've also seen Erin Brockovich, or also fertility in the near term,
Health span.
So really severe health issues related to, certain materials.
I think also, it's often not just the building materials, it's often the interiors, like the stuff that we add into to watch out for. I mean, in fires, like you mentioned, Las Vegas or others, it's often people die from the smoke. They don't die from the flames or from the heat necessarily, but for toxicity that's being released. So what we put in our homes, I think even beyond just the construction, it's relevant. And I think another issue, obviously, that came up during these fires now is the cars, and the electric cars and the batteries. And if you look at pictures of what they looked like after the fire, were completely disintegrated and melted into the ground. So I think those are things that we may not have considered as much as we should, probably.
Yeah.
Kishani, please.
Maybe just to add that, sometimes we talk about building for sustainability or building for climate change, resilience. There's this thing that comes to top of mind, that it's a cost issue, right? It's always sort of front of mind, how much is going to cost more. So there's always a trade-off in terms of the choices you make, and as Herwig was saying, like what you buy at a personal level, it has to be sort of really conscious, just like I think you mentioned about organic versus, like a banana you buy, it's the same thing. What you put in your house. There's the industry, the architecture, engineering, and construction industry, the AEC industry, has taken leadership in this, and you get things called product declarations, EPDs, environmental product declarations, that you can. There's data on that you can look at, and when you're buying something, to see if it's what its rating is. So. It's just like a label when you go to the grocery store and you look at the back of a product and you look at everything that's on that label. It's the same thing that a material has. So yes, it may cost, just like putting solar on your roof. There's a first cost, but as you go along, you get that return on your investment, so to speak. Similarly, the decisions that you make, and you sort of have that agency in terms of choices that you make, most likely will help you down the road.
Yeah, I think you bring up an interesting point of life cycle cost, and that's becoming more and more of an I think, a discussion that we as professionals need to have with our clients, because yes, initially the initial cost, either to protect against fire and or to reduce the amount of energy our homes are using, both in terms of insulation and kind of systems we put into it, might be slightly higher. But in fact, if you look at the life cycle of a building that's going to be there for 30 years, the construction cost actually is ridiculously small. It's around like 20%, and then the rest you spend on energy running the house. So if we are building responsibly, and I think being careful with our resources, yes, that will have a little higher initial cost, but it has huge reward. And I think in the long term, and I think specifically to the fire, I think it's also, it should make a difference in terms of like how you insure your house. If your house has like all these several systems in place, or is constructed more fire resiliently, your insurability also goes up, like in terms of like that there's, so I think it's probably also on an institutional level, there needs to be some adjustment and recognition from the insurance industry if that's being done. But I think as architects or as professionals, that's definitely a conversation you can have with a client and say you can install these materials and these are the advantages. Over a period of 10 years, this will be paid off and will have much bigger benefits to the thing. So I think it's important discussions to have, especially since we're rebuilding so many homes.
Mm. And as we are going to soon transition into Q&A, what you just mentioned, Herwig, rings a question we had online from Stephanie that was specifically asking about the responsibility of homeowners to ensure that, Stephanie asks whether a contractor should be updated. But actually, in response to this question we had online, there are codes and design professional informed, and this is their responsibility to ensure that the house or the structure that's going to be permitted meets all codes, right? They are codes.
And the codes have significantly changed. It's the problem is the housing stock that burned is sometimes 50, 60, 70 years old. And obviously those codes were not in place back then. But as you're rebuilding, so I think people can feel confident that the current building codes are actually quite adequate. I think, there can always be improvement and we can learn from it. But there, the type A roofs, what fire zone you're in, the city has, if you build anywhere close to where nature meets the city, so to speak, there's you have different kind of regulations for materials, etc. So I think a lot of the stuff is already in place, and it's I think that's obviously when you apply for a new building permit, that's gonna be required to fulfill.
And how did that work for a new structure? Kishani, you were the first ever 3D printed home in Los Angeles, and so how was this when you were on this frontier of codes or applications or experience from planning and planning the building department?
So we worked very closely with the city of Los Angeles, and to be honest, there was sort of, a whole village came around us, to be honest, to build this. It was not just myself and my colleagues or whatever. There was an entire group of people who helped us to bring it to completion. The city of LA, I think, for the most part, wanted to see if we were crazy, if this could be done. So they were a friend, actually, and we knew people who were sort of pushing that to see whether it would happen, where we would land. There were things that we would obviously do differently, like I was saying about the strength of the concrete. So there are things that we would really want to do in version 2, where the 3D printed concrete could be sort of the structural concrete. So right now, that concrete is not being used as structural concrete where the city is concerned. These are sort of things that we had to deal with, and Title 24, as you were speaking, the energy code for California is pretty high. It's pretty stringent. So you have to ensure that you meet those requirements to pass for energy. So, yeah.
What about the fire department? Did you have any
we have
fire
sprinklers.
marshals?
We have sprinklers inside. So we had to do a separate, I think it's called access and hydrants, and then we had to set up a separate permit for the sprinkler system. It was required for new construction, even though it's only. We permitted it as a single-family residence because we didn't want it just to be an ADU. We wanted, given the technology and how easy it is to navigate different configurations in kind of odd sites and unbuildable sites in a way, we wanted to leverage whatever land was available in the city and use this as a template. So we permitted it as a single-family residence and not as an ADU, meaning for an ADU you have to have an existing structure. So so there was a lot of learning that came from it. We've got overhangs because we were looking at really the shade during the summer and getting the warmth in the winter and what the depths of those overhangs need to be. But then there's a fire issue, right? I mean, we've dealt with the roof and embers falling on the roof because we have a metal roof, and then we've got this fire retardant insulation right beneath it. So layers, as I think Nate was mentioning. But then if you gets under the eaves, and then what happens? So there's learning to be done for sure in this sort of first generation. But overall, yeah, it was a bit surprising how, I mean, we had lots of corrections to do once we sent it for the first permit set. We came back with several corrections that we had to work with the city and get them passed, and here we are.
What a beautiful process. Before we start the in-person Q&A here with our attendees and we get those mic setups, I will ask one more question. I got my wire with Stephanie, she asked a lot of questions, by the way. Kudos, Stephanie. There was a question about neighborhood implementation. So it's a bit of a echoing the weak link kind of condition we talked about with Nate earlier. And so the question is, can we address the way in which the preventative or active solutions need to be implemented at the scale of the neighborhood for them to be effective? How can it be meaningfully, how can a meaningful scale be achieved? So if I understand it correctly, there's this discussion about something can only work if it's implemented at the scale of a neighborhood. What do you think is the best body of design or law that we can leverage here, and how does one good solution scale up?
I think the question may be getting at, I heard active systems, but I also think it may be getting at this notion of a fire-adapted community. So the truth is, we, like everything in life, we can't survive these types of events alone. It's very difficult to handle things when you're on an island. You need to bring things in, you need to get the resources, and a community is the same way. The reality of a community in a fire, though, is your neighbor's house could be the house that is completely not managed and resilient, and it poses a threat once it catches on fire that may be 10 times worse than the actual wildfire itself, locally. The wildfire is, you think about it, you see them all the time from the sky. You see this line of flames, and it moves through relatively quickly. But as it starts to ignite larger structures in a neighborhood, those are the things that cause these giant catastrophes that we just experienced. So you need your neighbors to be paying attention to what they're doing and be aware of it. And it takes people who are aware of what causes fires and what could make their home, susceptible to those fires. So the value of a fire-adapted program is that it educates the community and gets people thinking about things. My neighbor was doing a bunch of work on their house, and they cut some brush, and they didn't even realize that a bunch of the brush had fallen right under their eave, and it was completely out of their sight. But because I was above them, I could see it. So we mentioned it, and we worked together to figure this thing out. Now, there are no definitive studies that I'm aware of that can say, yes, in a fire-adapted community, we will have X% reduction in loss. But there is a general sort of allegorical understanding that this has significantly reduced losses in those communities who come together to create these fire-adapted communities. And this is why California and many other states are looking at and have implemented these insurance guarantees or even reductions in insurance if you are, for example, an NFPA Firewise community. But it's a process, and it takes designating the community and working together to become certified. And that's when you can start to see those insurance benefits. The real win is that everyone kind of comes away with a better understanding of what it means, what the problem areas are and what they can live with. And then you can start getting into a more advanced notion. The word active was mentioned. To me, active means systems that activate and include outside elements like water-based systems are active, whereas the structure itself is passive. Well, active systems on a community basis, what do you lose when you have a large fire? Well, you lose your power, you lose your water supply, and this is just physics, folks. This isn't someone did a bad thing and you don't have water. This happens in every major fire. It doesn't have to be a wildfire. It's just how much water can flow through those pipes. So one of the interesting things we saw in Herwig's slide was this notion of an underground tank. That is taking the pressure off of the community municipal system if you can also utilize that water source to protect your property, because otherwise it's going to sit there. I think I posted a picture of an aerial of Palisades, and you can see a bunch of full swimming pools next to the burnt down structures. Why not put that to work for you? Get a system, get a pump, make it part of an automatic system, even better. Automatic trumps manual, but we have to also work through code issues, because you can't be mixing that kind of water with the water that goes into your house. So there's a lot to think about, but as a community, you could set up ways and permitting processes to make that possible. You could have a community-based water tank, up on a hill or raised up. You could. There's so many possibilities. We have to be creative as we go into this, but the fire-adapted community is a great way to organize people around a common mission to protect their home. And so they don't have to go through what communities here are going through.
Be a good neighbor. As we're arriving very close to the end of the hour, we wanted to at least have one question from the audience. I know we have some mics going around. Oh, we shall use a mic.
Testing. Hi. So just I'm kind of acting prophylactically on my own house. I own a 1928 stucco home, Spanish style up in Glendale. And as you're describing everything, I'm realizing I need to move home and not rent it anymore and take every penny I have and do what I can to fix it. But what are the first things that someone who does not want to lose their home should do? Is it, just clearing away the brush 5 feet from the house and sealing all the windows? And what can we do that is not going to be extremely expensive, or, tear down the house and rebuild?
Sure. I could start. You want to take that?
Yeah, I can. Maybe as a part of it. I think there is probably different degrees of what you can do. I think, as was mentioned before, I think probably one of the biggest issues are the roofs. So to improve the fire resistance of your roof is one. There's also things that you can just make. Maintenance is a big issue, like to kind of go over your vents, everything that is opening inside the building, like an attic. You can improve that, and that's not very expensive. Any cracks in the house, we talked about improving it for smoke resistance. Those are all fairly small things that you can probably phase out or phase in over a period of time. More aggressive things would be to have like an exterior sprinkler system, but that's actually not something that's extremely expensive. It's just something that requires some planning. So I would say there's kind of a priority list, but I would probably start with making sure the house is well maintained, the gutters get cleaned out, your brushes, trimmed back, your cracks are sealed. Those are kind of like very basic things. And then the next one would be to improve the fire resiliency of the different kind of like surfaces of the project, of the house, like the roof. The walls also can be improved, obviously, with adding cladding to it, insulation, etc.
Yeah, I think the least expensive and probably, interestingly, the most efficacious thing you can do is get rid of shrubs within 5 feet of the house. Don't have the tree. Unless you have a non-combustible wall, we can look at it structure by structure, but don't have that tree growing into the house. Don't have the acacia. Acacias can do wonderful things, by the way, blocking embers, but when they're piloting ignition on your house, not a wonderful thing. The statistics are really interesting. So structural hardening is what we refer to when we're doing non-combustible siding or fire-resistant siding, the Class A roof. Those are all structural things, and those are really important. And there are numbers all over the place, but you can reduce losses by, say, 40% just by doing that. And that's irrespective of what's around you. Then when you look at modifying your landscape, thin it out. Just be smart about, don't put combustible furniture right up against your house if your house is combustible. Just move it away a little bit, give it a few feet. Deal with that fence attachment, make the last couple feet non-combustible. You know, this isn't huge money. Clean out your gutters if you have a tree above you. Get rid of the tree if it's a tree that constantly litters and you can bear to part with it. Some of us love that. The magic of some of the canyons is being in those trees if you live in a canyon or anywhere. But, you know, if it's other types of trees, you know, Italian cypress, have you ever seen one of those burn? It's amazing. It's like the 4th of July, and they produce, you know, 20 times more embers than what you saw in the video. So just be aware again of the vegetation, and that's usually not expensive to deal with in the short run, and try to clear it before the wildfire season. That's the cheapest thing. So with the vegetation and the structural hardening measures, you can get up to at least a 70 to 80%, you know, reduction in those losses. And that's based on actual fires. And you can further increase that by spending a bunch of money to kind of like get you to the end. But listen, I'd be happy with an 80% improvement any day if I only had to spend, you know, $1,000 on doing some landscaping work, or a few $1,000s depending upon your property. So.
Well, as we reach the end of our event, we wanted to thank you all for your sharing your experience, your expertise. We've been honored to have you all, and we're going to continue this conversation after the event ends. We are also extending an invite to join our Resilient Futures Task Force as advisors, because this is just the beginning, right? SCI-Arc and other schools around the city are activated, they're organizing, there's a lot of volunteering going on, and have you seen you all expend a lot of time in that space, and we're grateful for it as we plan for more resilient futures. So Herwig, do you have any closing thoughts you wanted to tell about this event before we close?
Yeah, I also wanted to thank everybody here for coming, sharing your professionalism and all your expertise with our community, and we're trying to support and help our community. We really appreciate your giving your advice and your expertise, and thank you. And I hope we will continue with that, and I hope this is helpful for everybody that was affected by this. Thank you.
All right, thank you.